Welcome to your deep dive into the world of symplectic geometry. It's pretty fascinating stuff, and we're going to be looking at some excerpts from academic papers that you sent us. Yeah, I was looking through them earlier, and I saw mentions of teardrop orbifolds and quantization of circuits, and even something about how geometry influences the way light dances at the bottom of a swimming pool.
Oh, wow.
So are you ready to jump in?
Absolutely. Symplectic geometry is really a powerful tool, and it can help us understand not just abstract mathematical concepts, but also real-world phenomena.
Okay.
It's like having a special lens that lets you see connections that you wouldn't normally be able to see.
Okay, so before we go too far, let's just start with the basics.
Okay.
What is symplectic geometry? I have to admit the term sounds a bit intimidating to me.
Yeah, it can sound a bit complex, but at its core, symplectic geometry is all about preserving area in a very specific way.
Okay.
So imagine you draw a shape on a balloon,
Okay.
and you inflate the balloon. The shape of the drawing changes, but the area inside those lines stays the same, right?
Right.
Symplectic geometry deals with spaces where certain transformations, like stretching or twisting, preserve this special kind of area that's defined by something called a symplectic form.
So it's not like the kind of geometry that we learned in high school with angles and lengths.
Exactly. We're not really interested in distances or angles. Instead, we're interested in how this special kind of area behaves when we change or transform the space.
Okay, so I think I'm starting to get it.
Good.
Now, I noticed in the paper, PRX quantum 0.5.0030309.pdf, there's this equation labeled 2.29.
Yes.
Is that an example of a symplectic form?
You're right on. That equation represents a Poisson bracket, which is an essential tool in symplectic geometry.
Okay.
And it's a close relative of something called Hamiltonian mechanics.
Mm.
You can think of it as a rule that tells us how different quantities in a system will change over time.
So how does all of this tie into Hamiltonian mechanics? Because I remember that from physics class as being about how objects move.
That's a great point. Symplectic manifolds, those are the spaces that we were talking about.
Okay.
They form the very foundation for Hamiltonian mechanics.
Okay.
They basically provide the setting to describe how particles and systems evolve over time.
Now, there was this one concept that I found really interesting.
Okay.
The idea that you don't always need canonical conjugate pairs of coordinates in Hamiltonian mechanics.
Right.
Could you just break that down for me?
Yeah, sure. It sounds like a lot of jargon, but it's actually a really fascinating idea.
Yeah.
So PRX quantum.5 by 020309.pdf goes into a lot of detail about this.
Okay.
It essentially means that we can analyze certain systems, like circuits, for example, without needing to define those pairs of variables that we traditionally rely on in classical physics.
Okay.
For example, the paper talks about inductively shunted islands.
Right.
And it shows how the principle of current conservation, so the idea that can't just disappear,
Allows us to understand how the circuit behaves.
That's really interesting. So what are the implications of being able to analyze these systems without using these traditional pairs of variables? Does it actually change how we think about physics?
It really is a game changer.
Okay.
It opens up a whole new world for analyzing and quantizing systems that were previously very difficult to handle using standard methods. This is especially exciting in areas like quantizing circuits, which is all about bridging the gap between classical and quantum physics.
Okay.
And, there's some cutting-edge research happening right now.
Yeah.
The papers 15, 16, and 17 in your source material highlight this work that's going on.
Wow. So symplectic geometry is kind of like this secret decoder ring.
In a way, yes.
That's helping us to unlock all these mysteries of the quantum world.
It helps us find those connections.
But wait, there's more, right? I keep seeing these terms, Lagrangian submanifolds and Lagrangian fibrations, and they sound very intense.
They're very important concepts, but don't be intimidated.
Just think of them as special subspaces within our symplectic manifolds.
Right.
These subspaces have the unique property that our special area, the one that is defined by that symplectic form, effectively vanishes on them.
So can you give me a more visual representation of that? I tend to learn better if I can picture things.
Sure. So imagine a soap film stretching across a wire frame.
Okay.
It forms a very smooth surface that wants to minimize its area,
Okay, right.
A Lagrangian submanifold is similar to that. It's like a surface in higher dimensional space or area, but the area is defined by the symplectic form, is minimized or preserved in a specific way.
Okay.
It's almost like the soap film is finding the most efficient way to exist in that space.
I think I'm starting to visualize it.
Good.
But why are these Lagrangian submanifolds so important?
They are essential for understanding how predictable or integrable Hamiltonian systems are.
Okay.
Do you remember Arno-Give.pdf
Huh?
and the principle of least action?
Yes, isn't that the idea that a physical system kind of takes the path of least resistance? Like a ball rolling down a hill will always choose the fastest route.
Exactly. So that paper connects the motion of a system to these special curves on a Lagrangian submanifold that minimize a certain quantity that is related to energy in time.
Okay.
So you could say those curves on that soap film,
Right.
they represent the most efficient paths that the system could follow. It's like the system is taking a shortcut through this space defined by the symplectic form.
So we're connecting how soap films behave to the motion of planets and the paths of light rays.
That's the beauty of symplectic geometry. You know, it reveals these surprising connections between things that seem completely unrelated at first glance.
This is really mind-blowing.
I know, it's fascinating.
But I think we're just getting started.
Yes, we are. And speaking of light, that brings us to a fascinating connection between symplectic geometry and singularities.
Singularities. Okay, now I'm really having flashbacks to calculus class. Weren't singularities those points where functions just went a bit crazy?
Yeah, that's a good way to think about it.
Okay.
So in this context, singularities refer to those points where things like wave fronts, you know, the leading edge of waves,
Right.
they become focused or they change very abruptly. So think about the ripples that you see in a pond after you throw a stone in.
Okay, I can picture that.
Yeah.
But how does this relate to symplectic geometry?
Well, it's all about how these wavefronts evolve and interact.
Okay.
And, you know, the source material mentions caustics.
Yeah.
So what about those?
Yeah, what about those?
Well, remember those really cool patterns of light that you see at the bottom of a swimming pool?
Right, like when the sunlight hits the water.
Exactly. So those are caustics. And their shapes are actually governed by the principles of symplectic geometry.
Wow, so you're saying that those pool bottom light shows are actually driven by complex math?
They are. The points where those patterns become super intense, you know, those really bright spots, those are actually examples of singularities.
That's so cool. But Arno-Give.pdf mentions something called the discriminant of the Weyl group.
Yes.
That sounds pretty intimidating.
It sounds complex, but it's essentially a tool for classifying the different kinds of singularities that can show up in wavefronts. Think of it like a catalog or a guide to all the ways light can bend and twist to create those really intricate patterns.
So it's like a mathematical Rosetta Stone to help us understand the language of light.
Exactly.
So what are the implications of being able to classify these singularities? Does it actually help us to understand light better?
Absolutely. Understanding these classifications helps us predict how light will behave in different situations.
Okay.
Which is incredibly valuable and feels like optics.
Makes sense.
And even astrophysics. Arno-Give.pdf even links this to the fundamental theorem of symmetric polynomials.
Okay.
Which is a really clever way of simplifying complicated equations.
Right.
It all comes back to finding those hidden patterns and order within seemingly chaotic events.
I see how it all connects now. We've gone from soap films to swimming pools, and now we're talking about the nature of light itself.
That's right. Symplectic geometry has these wide-ranging applications.
It's incredible.
Yeah.
But we haven't even talked about contact geometry yet.
Oh, yes, that's right.
Is that a whole other beast?
You could say that. Contact geometry is related to symplectic geometry, but in a slightly different way. So instead of preserving area, it's more about preserving direction.
Okay.
So picture yourself navigating a maze.
Right.
You can move forward or backward along a path, but you can't just suddenly decide to move through walls.
Right. That makes sense.
So that's what contact geometry is about, dealing with spaces where movement is restricted in a specific way.
Okay, that's an interesting way to think about it.
Yeah.
But Arno-Give.pdf talks about hyperplanes and a contact form.
Right.
Could you explain those in a way that makes sense to someone who isn't a mathematician?
Sure. So think of a hyperplane as a flat slice of a higher dimensional space. So in a 3D world, a plane, like a flat surface, is a hyperplane.
Right.
But in a 2D world, a line is a hyperplane.
Okay, I get it.
So contact geometry focuses on structures that assign a particular hyperplane to each point in the space.
Okay.
This defines which directions you're allowed to move in at that point. And the contact form, that's the mathematical way we define this whole structure.
Okay.
It's similar to how we use the symplectic form to define area in symplectic geometry.
Yeah. So Are symplectic geometry and contact geometry totally separate things, or do they ever kind of interact with each other?
They're definitely related, but Arnagiv.pdf
Mhm.
talks about the symplectification of contact manifolds.
Symplectification.
Yeah, it's basically a way of transforming a contact manifold into a symplectic manifold by adding an extra dimension.
Right.
It's kind of like turning a 2D blueprint into a 3D model.
Okay.
And this lets us use all those tools from symplectic geometry to work on problems in contact geometry.
That's really cool.
Yeah.
What kind of problems does this connection help us to solve? Why is it important?
It allows us to tackle those big questions about the behavior of dynamical systems,
Right.
which are systems that change over time.
Okay.
And, Arnagiv.pdf uses this connection to look into something called the Seifert conjecture. It's basically a question about whether certain types of flows on a sphere.
Oh, okay.
So imagine a continuous movement on the surface of a sphere
Right.
must eventually repeat themselves.
So it sounds simple,
Yeah.
but I'm sure it's more complicated than that.
Oh, it definitely is.
Okay.
This seemingly straightforward question actually has some really deep implications for how we understand the evolution of complex systems over time.
Wow.
But we've covered so much today. How are you feeling about moving on to moment maps?
My head is spinning a little bit, but in a good way. I'm
Yeah.
ready for more. Bring on those moment maps.
All right, let's do it. All right, moment maps. They might sound a little abstract, but they're actually a very elegant way to understand symmetries in Hamiltonian systems. So you can think of symmetries as patterns or regularities in the way that a system behaves.
Right.
Moment maps, they help us identify these symmetries
Okay.
and connect them to conserved quantities.
Observed quantities.
Yeah. So these are things that stay the same even though the system itself is changing.
Oh, so like the energy of a swinging pendulum?
Exactly.
It always stays the same, even though its position and speed are constantly changing.
That's a perfect example.
Okay.
The energy of the pendulum, it's a classic example of a conserved quantity.
Right.
And moment maps, they give us this mathematical way to actually represent those conserved quantities, which in turn helps us analyze and predict how the system will behave.
So can you give me some other examples of how moment maps work in the real world?
Well, LSG.pdf has some really good visuals.
Okay.
It talks about a spherical pendulum.
Spherical pendulum.
Yeah, like a regular pendulum.
Okay.
But it's free to swing in any direction.
Mm.
And the paper shows how the pendulum's angular momentum, which is another conserved quantity,
Okay.
can be represented by a moment map.
Mm.
It's like a way of visualizing how the pendulum's motion is actually constrained by its angular momentum.
So is the moment map like a map of all the possible paths that the pendulum could take?
You're thinking along the right lines. The moment map doesn't show the specific paths,
Okay.
but it does give us a geometric picture of the constraints that are acting on the system. LSG.pdf also gives another example of a torus, like a donut shape,
Okay.
acting on a sphere.
Okay.
The moment map shows how this donut action actually affects the geometry of the sphere.
Wait, a donut acting on a sphere? How do I even picture that?
I know it sounds strange, but imagine the donut rotating around the sphere in a particular way.
Okay.
The moment map basically captures how this rotation changes the sphere's shape and properties.
Oh, that's a pretty wild image.
It is, and here's the really cool part.
Yeah.
The image of this moment map, so the output we get from it,
Right.
has a special shape called a convex polytope.
Okay.
It's kind of like a multifaceted gem that contains all the essential information about the symmetry.
So we've gone from soap films and swimming pool lights to spinning donuts. This deep dive has been quite the journey.
It has been, hasn't
But
it?
before we wrap up, I'm curious about one more thing.
What's that?
LSG.pdf mentions that moment maps can be used in gauge theory.
Yes,
And I remember that gauge theory is all about understanding the fundamental forces in physics, right?
that's right.
Can you connect those dots for me?
It might seem like a big jump, but it turns out that all of these abstract mathematical ideas actually have real-world applications in physics.
Okay.
Gauge theory is the language we use to describe forces like electromagnetism
Yeah.
and the weak force. And these forces determine how particles interact.
Right.
Moment maps, they give us this powerful tool for understanding the symmetries that are built into these theories.
So we've gone from the geometry of spinning donuts to the forces that hold atoms together.
Exactly. It just shows you how wide-reaching symplectic geometry really is.
This has been an amazing deep dive.
It has.
Can we just do a quick recap of the key takeaways?
Yeah, sure. We started off by defining symplectic geometry as a type of geometry that focuses on preserving area under certain transformations.
Right, like stretching or twisting.
Exactly. And then we talked about symplectic manifolds, which are the spaces where this geometry happens.
Okay.
And then there were those special subspaces called Lagrangian submanifolds.
Right, like the soap film.
Yes, and these play a critical role in helping us understand how predictable systems are.
And we can't forget about the singularities.
Right, those points of intense focus.
We learned how symplectic geometry can be used to classify them and figure out how they behave.
Yeah, and then we moved on to the relationship between symplectic geometry and its sibling, contact geometry.
Right, which is about preserving direction.
Exactly.
And then finally, we explored the world of moment maps.
Yes, a powerful tool for understanding symmetries and conserved quantities.
Right, and we even saw how they can be applied to things like the spherical pendulum, the torus acting on a sphere, and even gauge theory.
It's amazing how it all connects.
This deep dive has definitely given me a new appreciation for geometry and its role in the universe.
I'm glad to hear that.
Do you have any final thoughts or maybe a question that I can ponder as I continue to explore this topic?
Well, we talked about how the quantization of circuits is possible, even without those traditional canonical coordinate pairs. What do you think the implications of this might be for the future of technology as we delve deeper into the quantum world?
That's a really great question. It makes me realize that this is just the beginning of my journey into symplectic geometry.
There's always something new to discover.
Thank you so much for being such an awesome guide.
It was my pleasure. Remember, knowledge is an endless journey of discovery.
That's a perfect note to end on.
I think so.
Thank you for joining us on this deep dive into the fascinating world of symplectic geometry.
Thank you.
Until next time, keep those brain gears turning.